When we think about an earthquake, we usually picture a building swaying back and forth, right? But what if I told you the movement that really brings buildings down, the most dangerous one, isn't swaying at all? It's twisting. Today, we're diving deep into one of the most critical and honestly often overlooked dangers in seismic design: plan irregularities and the absolutely destructive twist they can unleash on a structure. So, here's how we're going to break it down. First, we'll get to the bottom of what causes this dangerous twist. Then, we'll look at the 5 main ways buildings get it wrong. We'll see some tragic, real-world examples from a major earthquake, check out how the building codes are fighting back, and then wrap up with the best practices you need to know to design safer buildings. All right, let's get into it. To really get why a building would twist in the first place, you've got to understand this invisible tug-of-war that's happening inside the floor plan. It's a battle between 2 very important but invisible points. On one side, you've got the center of mass, or CM. Just think of it as the building's center of gravity. It's where all the weight is focused. And that's exactly where the earthquake's force is going to push. On the other side, you have the center of rigidity, the CR. This is the structural center, the center of stiffness of all the columns and walls. It's the natural point the building wants to pivot around. Now, in a perfect world, these 2 points line up exactly. When they don't, well, that's when you get into some serious trouble. Let's make this super simple with an analogy. Picture a playground swing. If you sit right in the middle, your mass is perfectly aligned. When someone gives you a push, you sail straight forward and back. Simple, predictable. That's a well-behaved, regular building in an earthquake. It just moves back and forth. But what if you scoot all the way over to one side of the swing? You've just shifted your center of mass. Now, when you get that same push from the center, what happens? You don't just go forward. You spin out in this violent, wild twist. That exact motion is what happens to a building, and that whipping action creates these enormous forces that punish the columns furthest away, pushing them way past the breaking point. Okay, so how does this dangerous gap between mass and stiffness even happen in the real world? Well, the seismic codes point to 5 main culprits, 5 types of plan irregularity that basically set the stage for this destructive twist. We're going to walk through these 5 troublemakers one by one. You've got mass asymmetry, stiffness asymmetry, a messy distribution of your resisting system, something called diaphragm discontinuity, and finally, those architecturally famous but structurally infamous re-entrant corners. First up, mass asymmetry. And a classic example, you see this all the time, is putting a huge, heavy water tank on the corner of the roof. That 120-ton load pulls the building's center of mass way over to the side. It creates this perfect lever arm, and when the ground starts shaking, that offset forces the entire building into a dangerous spin. Next up is stiffness asymmetry, and this one is probably one of the most common and hazardous out there. Just imagine a typical corner building in a city. You might have solid brick walls on 2 sides, but the other 2 sides facing the streets are all open with glass storefronts, right? Those super stiff walls pull the center of rigidity way over towards them, creating a huge gap from the center of mass. It's basically a built-in pivot point, just waiting for an earthquake to make it rotate. Then there's the non-uniform distribution of the lateral load-resisting system, the LLRS. Now, this one's a little more subtle. Imagine a long, skinny building, and the only strong shear walls are way out at the 2 ends. During a quake, the floor slab in the middle has to drag the seismic forces a huge distance to get to those walls. The center of the building starts to bow and deform, putting all this unplanned, intense stress on the columns stuck in the middle. Diaphragm discontinuity. This is all about the floor slab. The slab is supposed to be this rigid, solid plate that ties all the columns and walls together and spreads the load out. But when you start punching massive holes in it for things like atriums or courtyards, especially when those openings are over half the floor area, you're left with a weak, floppy diaphragm. It just can't transfer forces the way it's supposed to, and you basically disconnect the structure from itself. And finally, re-entrant corners. This is for any building that isn't a simple box. You know, your L-shapes, T-shapes, U-shapes. When an earthquake hits, the 2 wings of an L-shaped building actually try to vibrate on their own, moving in different directions at different times. This creates an unbelievable concentration of stress right there in that inside corner, stress that can literally tear the building apart. Look, this isn't just theory from a textbook. The tragic 2001 Bhuj earthquake in India gave us devastating real-world proof of exactly what happens when these irregularities are ignored. This is where the engineering gets very, very real. So many apartment buildings collapsed because of a classic stiffness irregularity, an open ground floor for parking, or what's known as a soft story. You had a stiff, solid wall at the back of the building and just a few flexible columns out front. The buildings didn't just sway, they rotated violently around that rigid back wall. The front columns were whipped so far, so fast, that they didn't just bend or crack, they sheared off completely. And that led to total pancake collapses. And here is our rope swing analogy playing out in the most tragic way possible. Investigators found buildings where a massive water tank on one corner caused a catastrophic torsional failure. The columns diagonally opposite that tank were hit with this incredible whiplash effect. The combination of twisting and gravity was so intense, it just pulverized the concrete at the tops of the columns, just shattered them. A school building with a classic L shape showed the re-entrant corner problem with terrifying clarity. The two wings shook out of sync, and all that stress was focused right at that inside corner. The result? A massive crack that ripped through the structure from the roof, through the slabs, all the way down to the foundation. And the really heartbreaking part is that a simple seismic separation gap could have saved the entire building. Now, in response to these kinds of devastating failures, engineering codes like India's IS 1893 got a lot stricter. They give us a clear, mathematical way to force designers to account for torsion whether they think they need to or not. The code's main weapon is this formula for design eccentricity. And the key idea here is actually pretty profound. You don't just design for the twist you can calculate on your computer. The code makes you design for an amplified, worst-case scenario. So let's break this down. It's got three key parts. First, you've got your E. That's the actual, calculated distance between the center of mass and rigidity. But then the code adds two critical safety nets. It adds a buffer for accidental eccentricity. That's to account for stuff you can't predict, like where people might put heavy furniture or equipment. And then, this is the big one, it forces you to multiply your calculated twist by 1.5. Why? Because the physics of a twisting building actually makes the forces even worse than they look in a static model. The takeaway is huge. You are required by law to design for a twist that is 50% larger than what you initially calculate. Okay, knowing the problem and the formula is one thing, but preventing it from the start, that's the real goal. So let's talk about the best practices for designing buildings that are resilient and safe right from the beginning. Think of this as your design playbook. Number one, and this is the most important, start with symmetry. If the architect absolutely needs an L shape, then break it into simple rectangular blocks separated by seismic joints. 2. Spread out your stiff elements, your shear walls, your columns, as evenly as you can. 3. Put heavy stuff, like water tanks, near the center. 4. Keep any holes in your floor slabs small and away from critical areas. 5. Run your 3D models early and make sure the building's first instinct is to sway, not to twist. And finally, number 6, architects and engineers have to be talking from day one to design these risks out of the project before they even become a problem. And before you finalize any drawing, just run through this quick sanity check. 1. Did you get that calculated eccentricity as low as possible? 2. Is your first mode of vibration a clean sway, not a twist? 3. Did you remember to apply the code's 1.5 amplification factor? And 4. If you're using seismic joints, are they wide enough so the building's sections don't just slam into each other? This is your last line of defense. Okay, so let's bring this all home. What's the ultimate takeaway for anyone designing buildings in a place where earthquakes are a real threat? If you remember anything from all of this, remember these points. Earthquakes make buildings twist. Asymmetry, in weight or in stiffness, is the enemy. The real-world consequences are life and death. You absolutely must design for an amplified twist, not just the one you calculate. And above all else, symmetry in your design is the most powerful weapon you have to create a safe building. And I want to leave you with this powerful mantra. You can run the most advanced software in the world. You can use the strongest materials known to man, but you cannot calculate your way out of a bad design. Good seismic performance is not about how complex your analysis is, it's about the simplicity and regularity of the building's shape. The strategy for safety starts, not in the computer, but on the very